Hello, students. We're gonna get started officially in a couple minutes. I'm just finishing getting some things set up. I saw that some of y'all were on here waiting, and I figured, hey, I might as well hop in here and see what's going on. Hope everybody's doing well. Say something to me if you're one of the, what do we have, 3 whole people? Do it in the afternoon when you guys want me to do it, and there's only 3 people here. But say something to me. Let me know who you are. Let me know who's here. And like I said, I'm just making sure everything is ready. Looks like it is. I've got sound. You should be able to hear me. This should work just fine. Got my water. Water, calculator, reference table. We're going to be ready to go, I think. All right. Let's see. Good afternoon, Emily. Excuse me. I'm so used to doing these first thing in the morning. Well, it's not first thing. It's first thing for you all, but for me, first thing is 6:30 or 7 or 7:30. All right. So let's see. What did I say I wanted to go over today? Because I certainly don't remember. What did I say? So this is the stuff we're gonna do. Looks like we're gonna go over the Unit 6 reference table quiz, which is pretty straightforward. It's just showing you where some things are. We're going to review ideal gas samples. Talk about those just a little bit. And then we'll have gas law practice time, which is basically where any of the questions that you guys have about gas laws from the worksheet. Hey, Tess. I will answer. So that's kind of our game plan for today. And it's now 1 o'clock, so we might as well get things rolling. Now, my wife has a Zoom meeting right now, so our bandwidth may be a little strained. I'm hoping not. We should be good, but if we have any issues, I'm going to handle it calmly, and it's going to be great. Yeah, we're gonna do gas law in a little bit. All right, but first, let's start by talking about this Unit 6 reference table quiz that you guys had yesterday. Yeah, it was yesterday. It shouldn't take us long to go over it. It's pretty straightforward. But I just figure we might as well talk about it real quick. Now remember, whenever we're doing a reference table quiz, all the stuff is going to be found somewhere on that reference table. So that's where you need to look. 1 through 3 are literally, can you read the reference table? And if you do, you'll see that standard pressure is on there, and they give it to you 4 different ways. Okay, so pressure, just like all things, is measured in a variety of different ways. And it just depends on what units you have. Just like speed. Here in America, we use miles per hour, mph, but in Europe, they usually use kilometers per hour. Different unit for the same thing. So standard pressure and temperature, or standard temperature and pressure, usually represented by STP, is something that we will talk about in a little bit. And it's something you may see mentioned, but all those values are on your reference table. So starting with standard pressure of a gas in atmospheres, well, it's pretty easy. It's just 1 atmosphere is going to be your standard pressure of gas. And again, I'm just looking at the reference table. Standard pressure in kilopascals, kPAs, it's going to be 101.3, which sounds like a radio station, but I don't listen to that radio station, so I don't know what it is. Next one, what is the standard temperature of a gas in kelvins? Okay. Fun fact, we have degrees Celsius, we have degrees Fahrenheit. There is no degrees Kelvin. It's just called Kelvin. Okay. It's an absolute temperature, which means, and that's the reason we use it so much in this unit. We don't use Celsius because you can have negative degrees Celsius. You cannot have negative Kelvin. There is no such thing as 0 Kelvin, and that's why we're able to use it in a math sense. That's why Kelvin exists. But absolute temperature is going to be 273 Kelvin, which you don't need to have this on your quiz, but that's equal to 0 degrees Celsius. Okay, so that's equal to freezing point of water, which, as you know, freezing point of water is dependent not only on temperature, but also on pressure. We learned about that last unit. Fill in the blanks in the following table describing thermodynamic variables. So we have heat of fusion of water and we have heat of vaporization of water. H subscript F, H subscript V are going to be our heat of fusion and heat of vaporization. Basically what this means is it's how much energy is required to melt a certain amount of ice. That's what heat of fusion of water is, and it's dependent on the mass. So we would expect to see units of energy and units of mass. In fact, I'll go ahead and tell it to you. Heat of fusion of water, which you know because it's on your reference table just like it is on mine, is 334 joules per gram. So, oh shoot, Tess, thank you. You saved me. That's why I like to do these. That's why I like to do it live so that you guys can correct me for those mistakes. So anyway, here we are. What was I saying? 334 joules per gram. That's how many joules it takes for 1 gram to melt. So if I had 1 gram of ice, it'd take 334 joules to melt it. Heat of vaporization of water. Same kind of thing, but instead of melting, which is what fusion means, vaporization means like evaporation. That's really what we mean here. So, or boiling. But that's how much energy you need to do that. Now, obviously, that takes more energy. It's a lot harder to boil something than it is to melt something. But so it's going to be 2,260 joules per gram. So quite a bit more energy. So what that means is if you had 1 gram of ice and you wanted to boil something, that means that you'd have to have 334 joules to melt it. Again, that's what fusion means. And then 2,260 joules to boil it. So that's what all that stuff adds up to. All right, complete the following temperature and pressure conversions. These are pretty easy. Whenever you're going from Celsius to Kelvin or Kelvin to Celsius, you're always going to use this magic 273 number. And the easiest way to remember it is that 0 degrees Celsius is equal to 273 Kelvin, which, by the way, you don't have to remember it. It's on here. Standard temperature, 0 degrees Celsius or 273 degrees Kelvin. So it's the same thing. So what that means then is if you want to go from Celsius to Kelvin, okay, hopefully it'll load here in a second. There it goes. You have to add 273. And if you're going from Kelvin back to Celsius, you're going to subtract 273. And again, both of those are based on that one relationship right there. So based on that then, I have a key here that I should be referencing. I don't need it. It's not real hard. But 0 degrees Celsius is going to be 273 degrees Kelvin. Again, that's straight from the reference table. And then 0 Kelvin is equal to negative 273 degrees Celsius. And again, when you're going from Kelvin to Celsius, you subtract 273. So for number 10 then, in my calculator, I did 450 minus 273. See, I'm using this relationship down here at the bottom. And I got 177 degrees Celsius. All right, next. 3 atmospheres is equal to how many kilopascals? So whenever you're doing these pressure conversions, you're not going to add or subtract. In fact, if you guys remember back in the previous unit, I taught you this. I said, whatever you, sorry, I don't know why I wrote 2. Whatever you're going from, whatever you're trying to get to, you make one of these conversion factors. Okay, and the reason is whatever you're going to, you put on top of the fraction. Whatever you're going from, you go on. It goes on the bottom of the fraction. And see, when you do that, from cancels, and to is what you're left with. So whenever you're doing anything other than Kelvin to Celsius, this is what you use. Because Kelvin to Celsius is addition or subtraction. Everything else is going to be either multiplication or division as a conversion. Okay, again, that's the word that we're emphasizing here, conversions. So, based on this, let's see what we're starting with in number 11. And I'm going to go through each of these 3 because it's an important skill to use, not only in this, but also back when we were doing moles to mass or moles to something to moles of something else. You still use the same thing. So, in number 11, we start with 3 ATM. That means atmospheres. And I'm trying to get to a certain number of kilopascals. So, when I set up my fraction then, what I'm going from is going to go on the bottom. See, from atmospheres, from goes on the bottom. And what I'm going to, kilopascals, is going to go on top. Now remember, whenever we use these conversion factors, we need to think of it as going like multiplying by 1. So If I'm multiplying by 1, that doesn't change the value. So remember, 12 eggs is equal to 1 dozen. 1 dozen is equal to 12 eggs. It doesn't matter which way you write those because you're still multiplying by 1 because the two things are equal. So if I look at my reference table, I can see that standard pressure is 1 atmosphere, and 1 atmosphere is equal to 101.3 kilopascals. So see, because those two are equal, we can multiply. When we multiply, atmospheres will cancel, and kilopascals we're going to be left with. And so I ended up getting, pardon me, I'm looking at my key because I don't want to calculate it. 303.9 kilopascals. So I got 303.9. I can write it over here, but I'm about to erase it. Okay, 303.9. Wow, that was a good 3. I know you guys missed my handwriting. So that's that. 12 and 13 are going to be exactly the same. Okay, exactly the same method. So let's take a look at number 12. 1500 mmHg, which what that really means is millimeters of mercury. So we have 1500 millimeters of mercury. Okay, and I'm trying to get to atmospheres over here. So I'm going to atmospheres. So same thing as before. Millimeters of mercury is going to go on the bottom because I'm going to want to cancel that here in a moment. Atmospheres is what I'm trying to get to. So that's going to go above the fraction. And so once again, I need to know, well, what is atmospheres equal to in millimeters of mercury? How do I make it a 1-to-1 type deal? And well, I just look at my reference table. I can see that 1 atmosphere, I have to sneeze. Hold on 1 second. Excuse me. 1 atmosphere is equal to 760 millimeters of mercury. Okay, and so once again, we can see that when we do this, millimeters of mercury cancels, and atmospheres is what I'm left with, so it works out. So technically, what you want to do in the calculator when you get to problems like this is you want to do 1500 times 1, obviously that's still 1500, then you divide by 760. And so when we do that, I get a value of 1.97. So I get 1.97 ATM. I'm going to go ahead and just write that over here. All right, same thing. Number 13, exactly the same thing. I'm still going to set it up the same way. I always start by writing what I'm given, which is 1200 torr. By the way, torr, T-O-R-R, is the modern way that we call millimeters of mercury. Millimeters of mercury is from the 1900s, back when we actually used to use mercury thermometers and mercury barometers. Okay, barometer is used for pressure, but now we don't because we found out mercury is bad. So torr, millimeters of mercury, same thing, but I'm still going to put torr down here on the bottom of my fraction. And I'm going to kilopascals. So kilopascals is going to go over here. So that means it's also going to go here. Remember, whatever I'm going to, it's going to go on the top. Whatever I'm going from is going to go on the bottom. And now I just fill in the information. And again, it's straight from my reference table because I know that 101.3 kilopascals is equal to 760 torr. All right. So in your calculator, you would do 1200 times 101.3, enter. Okay, you'd hit enter on your calculator, and then you divide that by 760. And when you do it, you get 160 kilopascals. How do I know that I get kilopascals as my unit? Well, because torr just canceled, and I was left with kilopascals. Kilopascals did not get canceled out. So my answer, 160 kPAs. All right, down here, this is really easy. I'm just going to burn through it really quick. All this stuff comes from, again, straight from the reference table. You have a whole table, one whole section right here that has to do with just water. So the first 3 rows are based on this section for water right here, which has specific heats for that. And then down here, you have a whole table of metals. And all those metals have specific heats as well. So I'm just going to burn right through this. You get it? Heat joke. And you guys can double check me later. But again, it comes straight from the reference table. So there's that one. Water vapor is 2.02 joules per gram degrees Celsius. Solid water is 2.05 joules per gram degrees Celsius. Titanium, 0.523 units, still joules per gram degrees Celsius. And honestly, I didn't need to write all these units. The unit is actually written in the table, so technically I don't have to, but you know what? I already started, so I'm going to go ahead and finish that way. Magnesium, 1.023 joules per gram degree Celsius. And then the last two, you're given the specific heat. You have to determine what the substance is, and it's aluminum, and it is pronounced aluminum, not aluminium, because we live in America. And then we have lead as well. So there you go, piece of cake. I don't think there are any questions about this, so I'm going to go ahead and move on to the next thing. So we are going to spend time on gas law examples. I do want to talk about gas law just briefly first, and I actually want to look at the bell. I'm sorry, not the bell work. I mean, we can, but it's pretty easy. If you guys want me to go over bell work, how many people are in here? 4 of you. Wow. I really was hoping that by doing it in the afternoon, and guys, I'm so happy to see the 4 of you here, but I was really hoping that by doing it in the afternoon, we'd have a little bit better participation. But if you guys do want me to go over the bell work, I will here in a minute. Just type if you want me to. But I want to talk about these 2 samples. Those are based on the ideal gas notes, okay, which you should have already taken. But I'm just going to talk about it real quick. Excuse me. So, ideal gases. What makes them ideal? Well, we have to make a lot of assumptions about them. If you want to know about that, you can find out more on your own time. But by saying something is ideal, we're just assuming a lot of things. Now, you might be thinking, well, Mr. Aaron, are ideal gases really like that in real life? They're pretty close, at least at standard temperature and pressure. They typically act like ideal gases. But all of this is based on one equation, the equation that I call pivot. Because that's the way I think about it. But it's PV equals nRT. Now, that exact equation is on your reference table. Okay? And here it is. It's number 1, 2, 3, 4, 5, 6. It's 6th underneath formulas. And it says PV equals nRT. Now, P, that's pressure, obviously. V, that's volume. N stands for number of moles. Okay? R is an ideal gas constant. More about that in a second. And then T is temperature. Now, if you look back on the front page, they have different values for the gas constant. They have one value, and again, I'm on the front page of the chemistry reference tables, front page of the green sheet that I know you guys miss. And I have one that's 0.0821, I have one that's 62.4, and I have one that's 8.314. And it's at this point, usually students say, well, if there's 3 of them, do we just use all of them? Do we just pick one to use? How do we know? It's based on the units. Okay, it's based on the units. Just like if you're here in America, we use dollars, okay, to buy things. And you go to Canada and you use maple syrup dollars, I assume. Or you go to the European Union and you use a euro. Depending on where you are, okay, you use a different currency. Depending on what units that you're given in ideal gas law, that's going to determine which number that you use. So R, okay, R is the most important part of this that you've got to keep track of. The one thing that's not going to change, okay, is N is always going to be moles. Okay, it's always going to be moles. That's going to be the unit. T is always going to be Kelvin. And the reason we do that, the reason it's always going to be Kelvin, is that if you had, I don't know, 0 degrees Celsius, and you're at freezing, which happens a lot. Remember, standard temperature is 0 degrees Celsius. And what that means is this whole term would just go to 0. And that'd be ridiculous. So mathematically, okay, we don't use Celsius. You have to use Kelvin. Tess says Canada money is monopoly money. That's right. It doesn't really count for anything. It is really colorful, and I'm not kidding. I actually do think I remember them saying, hearing about it or reading about it, that one of their dollar bills you could rub on it. It does have a maple scent to it. By the way, guys, I don't recommend you go around smelling currency. Okay, there's kind of a virus right now, so don't put that too close to your face. All right, pressure though. Pressure and volume are the ones that are going to change. Pressure, as we've already talked about, can sometimes be ATM, sometimes mmHg, sometimes kPa. Okay, it's going to change. Volume, okay, volume is typically just going to be liters. Okay, so I'll write that right here. Volume is typically going to be liters. Now, yeah, they could end up trying to trick you with something else in higher level chemistry, but for our class, It's always going to just be liters, okay? But it's pressure that's going to change, okay? So it's going to be one of these over here. And so based on that, that's how you decide which one you use. So for instance, say you have a problem, okay, that's using ATM. All right, maybe we have a problem that's using ATM. Now, no, that does not stand for automatic teller machine. It's atmospheres. But if you're using atmospheres, then I look at my R values and I see, oh, 0.0821 has atmospheres in it. Technically, it's liters times atmospheres over moles times Kelvin. That's the whole thing. But see, atmospheres right there, ooh, that looks terrible. Atmospheres right there is what tells me that's the correct R value to use. And again, we'll get more practice with that as we do a few of these problems. So let's start with number 1. Remember, 5 steps, guys. This is a 5-step problem. All right. So if the pressure exerted by a gas at 25 degrees Celsius and a volume of 0.044 liters is 3.81 atmospheres, how many moles of gas are present? So in this problem, they just gave us a lot of information. We have to be able to determine, okay, what are they actually giving us? So step number 1, as I hope you all know, is to write what you know. Write down what you're given. And guys, I've seen a lot of you where you're doing this. You just said, I got 25, I got 0.044, and I got 3.81. Okay, that's what I know. Guys, that means nothing. That means nothing until you start to put some context around it. First of all, 25 what? Watermelons? We have no idea of knowing because you didn't write the unit next to it. Is it $25, okay, which is worth $25, or is it 25 maple syrup dollars, which mean nothing? You have to know what the units are. So this is going to be 25 degrees Celsius, all right, 0.044 liters, and 3.81 atmospheres. Okay, so they're giving us a lot of stuff, but you need to do one more thing. One other thing that I recommend, remember, these are units, okay? All these things, degrees Celsius, liters, atmospheres, those are all units. But another thing that's worth writing is the letters that they represent. So 25 degrees Celsius, that's representing temperature. So I'm going to do T equals 25. 0.044 liters, that's going to be volume. So I want to say V equals this. 3.81, that's going to be P equals. That's the pressure. And the reason we do this is so that when you get to step number 4 and you're plugging things in, it tells you exactly where everything needs to go. It tells you exactly where everything needs to go. All right. Sorry. So there's one more piece of information that they give us that the problem doesn't actually say, and it's the it's the gas constant. Now again, I need to look at my gas constants and decide, okay, can I use 62.4? Do I use 8.314? No, we use this one, 0.0821. And the reason why is because of this right here, atmospheres. Because we're using atmospheres in this problem, I have to use a gas constant that has atmospheres in it. And I'll show you why in a second. But for now, just know it's going to be atmospheres. So the full units for that gas constant are going to be liters times atmospheres over moles times Kelvin. If you don't believe me, I'm looking at it. It's on the reference table. It's straight from that. So I'll write it out. Step number 1, good. Step number 2, what the heck are we looking for in this problem? And it says, how many moles of gas are constant? Now, another thing that I've seen throughout many years of teaching is students will go like this. No, yeah, that's a little helpful because you know what you're looking for, you have a target, but that's not how I want you to do it. We don't say moles. In the equation, it says N is what represents moles. So I want you to say N equals question mark. And that's because in step 3, literally what I'm doing is I'm just saying, okay, what equation do I have that has T, V, P, R, and N in it? I'm looking for an equation that has all 5 of those things and nothing else. And so that's when you say, oh, well, it's pivinert. Good old pivinert. And I'll go ahead and write it out right now. So look, then you can go through and be like, all right, do I have pressure? Yeah. Do I have volume? Yeah. Do I have N? No, but that's okay. That's what I'm looking for. Do I have R? Yes. Do I have T? Yes. That is why we write all this stuff out in a certain way. All right, so moving speeding up a little bit. This is the thing that I got the most questions about over the last couple days, is that when you guys are doing this math, I recommend, in fact, if you watch my video on, what was it, Friday? Yeah. I recommend that you do it with letters only. Okay, so like you stop right here and say, okay, what am I solving for in this problem? I'm looking for N, I'm looking for number of moles. Okay, then I need to get that on one side of the equation and everything else on the other side of the equation. That is the way I recommend doing it. That's the way the math teachers recommend I teach you how to do it. So do it with letters only. So we have got to isolate the variable we're looking for, which in this case, as I've already said, is N. This problem is not that hard. We say, all right, we got N times RT. Well, let's just divide out RT. Okay, and when I do that, you'll see RT is going to cancel. And if I do something to one side, I hope you're saying at home right now, you do the same thing to the other side. That's right. So I'm going to divide by RT over here as well. So I divided by RT because I was multiplying by it. You do the opposite thing to cancel it. Whatever I do to one side, I do the other side. You know, algebra. And so I ended up getting this. That's what I ended up getting. And that, now this one's pretty easy. I'll say that the combined gas law stuff gets a little confusing because you've got like a P over here and a P over here, and a V and a V and a T and a T. I know it gets confusing. That's all you do. Whatever you have to do to get something to the other side, you have to do the opposite. Whenever you do it to one side, you do it to the other. And honestly, guys, I can't teach you the algebra, okay? I can't teach you that. All I do is teach you the chemistry, but I can tell you that. All right, so now that we have everything written out, on step number 3, do I have the variable I'm looking for by itself? Yes, and everything else is on the other side. So now we can go on to step number 4, plug and chug. So I'm going to put everything where it needs to be. N, do I know it? No, I do not. So I'm going to just write it out as N. But I do know P, so I can say P is 3.81, and it's going to be ATM, 3.81 atmospheres. Do I know V? Yes, 0.044 liters. Okay, next, do I know R? Yes, I do, 0.0821. And the units are going to be liters times atmospheres over moles times Kelvin. And if you're saying right now at home, oh, but Mr. Nairn, that's so much stuff to write. Do we really have to write that? Yes, you do, and I'll show you why here in a second. And then last, we have T for temperature. Temperature is always measured in what? Kelvin. I wrote it up here. Okay, here, let me circle this really obnoxiously so you'll see it. Temperature is always going to be in Kelvin when you're doing gas law problems. So if you're saying, but they gave us Celsius, what are we going to do? I just told you, you add 273 to it. So all I'm going to do is that right there. 25 degrees Celsius plus 273, I get a number. I don't actually know what it is right now. Probably 290, 298, but I'm going to double check. What do you know? It's 298. So my new temperature value that's actually useful, okay, is actually going to be 298 Kelvin. And that's what I want to plug in. Okay, so I'll come over here. 298 Kelvin. Now listen, the reason Kelvin is so important, the reason getting the right gas law is so important, is because the units are all going to work. But let's go ahead and write out our answer for step number 5. So what do we end up getting for N? Well, let's see. In my calculator, I'm doing 3.81 times 0.044. I'm hitting enter. After I do that, I'm going to divide by 0.0821. I'm going to hit enter. And then lastly, I'm going to divide by 298, and I'm going to hit enter again. And I get a really little number. I get this, 0.00686. That's good enough. Now, units. We know, because the problem told us, how many moles is what we're looking for. But let's make sure. Let's make sure that everything worked out. So look, atmospheres is on top of the fraction right now. Atmospheres is also in the bottom of the fraction. And so atmospheres cancels. That unit is canceled out. Liters is in the top. Liters is also down in the denominator. That also cancels. And then look, here's Kelvin. Here's Kelvin again in the denominator within that ideal gas, the gas constant. So everything cancels out except for one thing, and that's moles. So what is my unit going to be? Moles. So if you're looking at that number and you're like, oh, but that number just seems wrong because it's so small. Remember, guys, we learned moles is based on mass, okay? And from what we know, gases don't weigh a whole lot. So we would expect to have very few moles, all right? So that's the answer to problem number 1. If you have questions, feel free to type them in. I'm going to get a sip of water. I said sip. I really meant chug. Nobody's saying anything about the bell work, so again, if you really do want me to go over the bell work, any of the two, oh Lord, any of the two of you that are here, type something. Otherwise, I'm going to go over number 2, and then we'll go on to gas law practice, like that worksheet. We'll go over the worksheet. All right, no questions? I've waited about 30 seconds. That's usually what the delay time is. Okay, I'm going to go ahead and move on to number 2 then. Move on to number 2. It says determine the Celsius temperature of 2.49 moles of a gas contained in a 1 liter vessel at a pressure of 143 kilopascals. Now, I'm going to read it again. Excuse me, I'm going to read it again. Determine the Celsius temperature. So already I know what I'm looking for. I know I'm looking for temperature of 2.49 moles of a gas contained in a 1 liter vessel at a pressure of 143 kilopascals. So they gave us a lot of stuff. Now I'm going to move a little bit more quickly this time, so make sure you can keep up. Step number 1, write out the stuff they gave me. They gave me 2.49 moles. I know that moles in the ideal gas law are represented with lowercase n. So I'll say, okay, n equals 2.49 moles. They gave me a liter, 1.00 liter. I know that's going to be volume, so I'm going to write it out. V equals 1.00 liters. Next one, pressure. Pressure is equal to 143 kPas, kilopascals. And it even says pressure. The word pressure is right there. So I know, I know it's pressure. All right. Next thing, is that it? And you may say, yeah, that's all the numbers the problem has. Remember, guys, okay, if it starts to look like an ideal gas law problem, go ahead and assume that it is. But we're going to need the gas constant. So, gas constant. Again, which one are we going to choose? All right. Remember, the units for pressure decide it. Moles are always going to be measured in moles. In this class, volume, always going to be liters. All right. The one thing that changes is pressure. So, if you look at your list of gas constants, is there one that has kPas in it? Yes, there is, and it's this one right here. 8.314 liters times, there it is, kilopascals over moles Kelvin. All right, so there we go. That's everything. And so, step number 2, what are we looking for? We are looking for temperature. It says determine the temperature, so we know that's what we're looking for. Next thing, step number 3, we write out the equation. It's the same old equation as before, but we're not looking for N here. All right, we're not looking for number of moles like we were in the last problem. We're looking for temperature. So we need to get T, temperature, by itself. I'm multiplying by R and N, so if I divide by N and R, that cancels it. Whatever if we're multiplying, dividing is the opposite. That helps me cancel it. And as you guys know, whatever you do to one side, you have to do the other. So I'm going to divide by NR over here. So when I do that, I get this. T equals, okay, let's see, PV over NR. And there we go. T, the variable we're looking for, is isolated. Everything else is on the other side, which means I'm ready to move on to step number 4, where we write some stuff in. So now I'm going to start plugging in numbers. Pressure, I can see right there, it says 143 kilopascals. Volume, 1.00 liters. Okay, and I'm going to divide all this by number of moles, 2.49 moles. And R, which R in this problem is 8.314. And it has a bunch of units, which we do need. I'm going to go ahead and write them all out. I'm trying to do a better job than that, though. kPa over moles times Kelvin. There we go. There's all the units. So I'm going to go ahead and do the math in my calculator and find out what all this is equal to. So T is what I'm looking for. Let's see what I get. In my calculator, I do 143 times 1. Wow, it's 143. Then I'm going to divide by 2.49 because that's on the bottom. And I'm also going to divide, again, I'm going to hit enter, and then I'm going to divide again by 8.314. Whatever order of operations you decide to use, which honestly, if I were not teaching right now, I'd be using lots of parentheses and doing it all in one line. If you're not comfortable with your order of operations, only do one thing at a time. Okay? Multiply, enter. Divide, enter. Divide, enter. Whatever it takes. So I get a temperature of 6.9. Okay? Wow, that's cold. Technically, you could make it 6.91 if you want. And it's at this point you're going to say, well, Mr. Noonan, 6.91 what? Okay. The problem says Celsius, so it's going to be really tempting for you guys to go, oh, this is degrees Celsius. No, it isn't. Let's take a look at the units we had in the last part of the problem. So look, we had kPAs on top, we had kPAs on bottom, so that got canceled. We had liters on top, we had liters on bottom, that got canceled. I had moles down here, I had moles right here, that got canceled. The only thing that didn't get canceled was Kelvin. So my unit right here is actually Kelvin. Is that what the problem is looking for? No, it wants Celsius for some reason. And so whenever you're going from Celsius to Kelvin or Kelvin to Celsius, that 273 number comes in handy. In this case, I'm going to subtract 273 in order to get my Celsius value. So it's going to be really small. So this is going to be negative 266.1 degrees Celsius. There's my answer. I'll box it. Okay, if there are no questions on this, okay, we will go ahead and move on to something else. Let me see if anybody is watching. Yay, we're back to 4 people. I am so happy. All right. All right, if there are no questions on this, I need you guys to tell me what problems you would like me to go over. And I did an oopsie. Usually when I'm teaching regular school, I have an academic version and I have an honors version of the 2 gas law problems. And I really shouldn't have done that. I really shouldn't. I should have just picked one and made that the thing that everybody was using, but I didn't. So if you guys have questions for me, I'll answer the correct one based on what class you're in. And if you're saying, oh, but missionary, you're going over a problem on the honors worksheet, I don't even have that. Or oh, you're going over something on the academic worksheet. I have the honors one. Still watch me do it. I'm gonna go pretty quick on these. Still watch me do it. It's gonna help you. All right, it's gonna help. So guys, seriously, now the time is open. If you have any questions you want me to go over, you need to pick one and I'll go over it right now for as long as it takes for 30 minutes. Okay, so let me know. What questions do you have? Waiting on you guys. And be specific, because the numbers do switch over down here at the bottom. So like if you're saying I need, here we go. All of part 2? Ugh, can you pick one first? Pick one. 4 and 5. Emily, which part are you talking about? Part 1 or part 2? In standard, right. But is it part 1 gas laws or is it part 2 ideal gas law? I have a feeling you mean 4 and 5 right here. But please let me know real quick. You guys got to let me know something. You got to tell me. All right, I'm going to go ahead and, okay. So Emily, I'm going to go over these 4 and 5 really quick tests. You go ahead and pick one, okay, that you want me to do on your worksheet. And again, be specific. Part 1, number what? Okay, part 2, number 1. All right, Emily, let's look at number 4 first. It says a sample of air in a syringe exerts a pressure of 1.02 atmospheres. That seems important. Okay, so I'm going to highlight that. At a temperature of 22.0 degrees Celsius, the syringe is placed in a boiling water bath at 100 degrees Celsius, and the pressure of the air is increased to 1.23 atmospheres by pushing the plunger in, which reduces the volume to 0.224 milliliters. What was the original volume of the air? Yes, Tess, I'm going to do that in just a second. I got you. So in this problem, they sure did give us a lot of numbers. That's because this isn't ideal gas law. Notice they said nothing about number of moles. They said nothing about any of that. So we know we're dealing with combined gas law, and they gave us a lot of stuff. So let's start writing it down. All right, first number that I see is 1.02 atmospheres, and I know that that is the initial. That's number one. You got it, Egypt. I'll do that one too. You guys go ahead and get your requests in, and I will get to them in order. So 1.02 atmospheres, that is P1. The reason I know that is that's what the pressure was that we started with, okay? It was exerting a pressure of 1.02, okay? At a temperature, so here's T1 of 22.0 degrees Celsius. Is that useful? Heck no, because we need it in Kelvin. Not a huge issue. I'm going to add 273. And I'm going to get that number in just a second. I don't know why I'm using a calculator. I knew that was 295. This is 295 Kelvin. So I got that number taken care of. I got this number taken care of. The syringe is placed in a boiling water bath at 100 degrees Celsius. So here's T2. They're giving us the second temperature. And this is going to be 100 degrees Celsius, which again, I want it in Kelvin. So I get 373 Kelvin. Okay, so there's the important one. And the pressure is increased to 1.2. So pressure 2 is going to be 1.23 atmospheres, which reduces the volume to 0.224 milliliters. All right, so V2. Now, how do I know that's V2? Because they said that's what happened. You did this, pressure became this, temperature became this. So, and also I know that I'm looking for original volume. That's going to be V1. So V2, 0.224 milliliters. Okay. So what am I looking for? What is the original volume? So I'm looking for V1. Now, I will tell you, I think most of you are pretty good at doing that right there. Steps 1 and 2. And honestly, I think that's hard for a lot of students. When I teach physical science, that is what students struggle with, just 1 and 2. But I think what's tripping a lot of you up is when you get to step number 3 and you have to algebraically figure out, oh, okay, what equation do I need? How do I get V1 by itself? So I know that's hard. I'm going to do the best I can, but honestly, and I mean this respectfully, that's not my job to teach you guys algebra. So I'll do the best I can. So I know this is going to be combined gas law because look at that list. Look at all that crap they give us. So I know automatically that I'm going to need all these things. And I know I'm trying to isolate V1. I'm trying to get V1 by itself. So first thing is I'm going to say, well, I got T1 down there in the fraction. Okay. So I'm going to say, well, T1, if I'm dividing by T1, multiplying by T1 will cancel it. And as you guys know, whatever you do to one side, you have to do to the other side. Okay, let me go ahead and rewrite what we got. So at this point, P1 V1 equals P2 V2 T1 over T2. So we got all this junk. And again, we're trying to get V1 by itself. So instead of multiplying by P1, dividing by P1, right, is going to help me cancel it. And so P1 goes away. So finally, what I get is V1 is equal to P2 V2 T1 over T2 times P1. That is the hardest part, okay? And so now I'm going to start to plug some things in really quickly for step number 4. Wow, that was a good number 4 I just drew. Now, do you guys see why it's so important to write everything out like that in step number 1? Because I've already done the logic part of it. Now it's just plugging things in. And this is where students get confused. Students that aren't doing step number 1 or aren't doing step number 2, when they get to step 4, they're just like, well, I guess I'll just multiply all the numbers. Or they'll go, well, I guess I'll just divide all the numbers. That's not how it works. This tells you exactly where everything needs to go. It's perfect. So P2, 1.23 ATM was P2. V2, I look at my list, 0.224 liters. T1, I look at my list, 295 Kelvin. That is important. Make sure it's Kelvin. All right. Next thing, I'm going to divide all this junk by T2, which is going to be 373 Kelvin times P1. P1, 1.02 ATM. So see, everything goes where it's supposed to be. Now we got to do a whole bunch of stuff in the calculator. So in my calculator, I'm going to go ahead and do 1.23 times 0.224 times 295 and hit enter. And then I'm going to divide by 373 and I'm going to divide by 1.02 and I end up getting 0.21 as my answer. So step number 5, I'm going to squeeze it in right here. V1 equals 0.21. And it's at this point you guys are probably saying, well, Mr. Aaron, 0.21 what? Well, let's look. ATM, ATM, canceled. Okay, Kelvin, Kelvin, canceled. And by the way, it wasn't liters. I can't believe you guys didn't say anything. Usually students are so quick to call me out when I make a mistake. That was actually milliliters is what it gave us in the problem. So my unit that I'm left with then is that milliliters. So my answer, 0.21 milliliters. Okay, I'm going to quickly do number 5 in the same way, but that's how you do it. If you want to replay it later, you can. Let's look at number 5. An unopened, cold 2.00 liter bottle of soda. Okay, so or soft drink. Okay, if you're my family, we call them soft drinks. Okay, and then my step grandfather calls them sody pop because he's from New York State. Yes, he does. He does say sody pop. He actually just called it pop. Contains 46.0 milliliters of gas, confined at a pressure of 1.30 atmospheres and a temperature of 5.0 degrees Celsius. The bottle is dropped into a lake. I'm assuming the Loch Ness Monster doesn't eat it, and it sinks to a depth at which the pressure is 1.52 atmospheres, causing the volume of gas to increase to 39 milliliters. What? I think they mean decrease. Yeah, I'm going to change that because that should mean decrease. See what I mean? That doesn't really make sense. So anyway, that's what we get. What is the temperature? So here's our target. What is the temperature of the water at that depth? All right, let's write some crap out. Let's see. I did that color last time. I'm going to do this color this time. Okay, so here we go. Is the 2 liters important? Okay, and you've got to ask that question first. And the answer is no, because as you guys know, a 2-liter bottle of soda has a lot of liquid in it and a little bit of gas in it. So because we're doing gas math, let me double check. Is this a gas worksheet? Yes, it is. Gas laws. So I don't give a crap about the other liquid stuff. I am only interested in this number right here, okay, and this number right here when it comes to volume. So that 2 liters is a trap. Okay, insert Admiral Akbar meme here. Okay, so cold 2 liter, we don't care. So what that means then is that V1 is actually 46.0 milliliters. Confined at a pressure, okay, P1, 1.30 ATM. At a temperature, there's T1, 5.0 degrees Celsius. And once again, guys, do we use degrees Celsius when we're doing gas stuff? No, we do not. So I'm going to add 273 to it, and I'm going to get 278 Kelvin. All right, so that's my actual T1. Next thing, we got V1, we got P1, we got T1. What's next? It sinks to a depth where the pressure is now. So here's P2. Okay. Here's P2 is 1.52 ATM. Okay. And the new volume, V2, is going to be 39 milliliters. So there you go. There's our new list of stuff. And so, what are we looking for in this problem? What's step number 2? What are we actually looking for? What is the new temperature? So what's T2? And guys, I'll go ahead and tell you, this is going to be one of the trickiest algebra. In fact, this is the trickiest the algebra can possibly get. So I'll show it to you real quick. That's a P. There we go. In fact, I bet my wife's students struggle with the same type of algebra. I'm not doing that junk because that's not how the math teachers recommend that it's taught. So anyway, we got to get T2 by itself. And the reason students struggle is because it's on the bottom of the fraction. You end up thinking that you can just divide away P2 and V2. That's not how it works. You can, but if you divide away over P2, V2, then what you actually end up getting is this whole side becomes 1 over T2. And that gets kind of confusing for students. So there's 2 ways you can do it. Step 1, or one way, is you know that this does the inverse. So if you do both sides to the inverse, then what that does is it gives you T1 over P1V1 equals T2 over P2V2. That's technically correct. And then what you do is you multiply by P2V2, same thing over here. And when you do that, cancels this, and then you get the correct answer, which is this. T2 equals, oops, that's a 2, guys. Sorry about that. T2 equals P2V2 T1 over P1V1. That is technically correct algebra. So if you like, that's one way you can do it. But a lot of students don't know how to use the inverse relationship. So the other way that I teach it when you're looking for a temperature, see if I can carefully erase everything that I don't want. There we go. Is multiply T2 over. So another way you can do this is you can say, all right, well, I'm going to multiply by T2 because I want to get it out of that fraction. I want to kill that fraction. By doing that, it cancels T2, but it's also going to put T2 over on this side. That's okay. So now what I have is P1, I'm going to put T2 over here, V1 over T1 equals P2 V2. And then the rest is really not that bad. Same thing. I want to get rid of T1. I'm dividing, so the opposite of dividing is multiplying. Cancel, cancel. Whatever I do to that side, I got to do to this side. Now I'm going to rewrite all this junk. So T2, P1, V1 equals P2, V2, T1, blah, 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 blah. And so the last thing I want to do is if I divide by P1, V1, that cancels these items. Whatever I do to that side, I got to do to this side. And so I end up getting the same thing. T2 equals P2 V2 T1 over P1 V1. The important thing is this, guys, because I know time is short and you guys don't want to hear me talk about algebra this much. But what's important is this. Whatever the problem ends up giving you, okay, however you need to get there, you do what it takes to get the final answer. When I was your age, I didn't do all this stuff algebraically. In fact, what I did is I just plugged in numbers and did mathematically what I knew I had to do until I got the right thing. So I still did the algebra, but I did it one piece at a time, and I did it with numbers, and that worked better for me. You guys do what you think you need to do. But there you go, T2. Step number 4, plugging all this junk in. That's going to take me a minute. T2 is what I'm looking for. P2 is 1.52 ATM. V2, and again, see how helpful it is to have that list, because now I'm just going to the list and I'm putting everything where it needs to be. V2 is 39.0 milliliters. Okay, next thing, T1. T1 is 278 Kelvin, and remember guys, if I haven't said it enough, Kelvin is important. Make sure you use Kelvin. Next thing, P1, that's going to be 1.30 ATM. And next, I'm going to have V1, which is going to be 46.0 milliliters. So there you go. Everything's been plugged in. Step number 5, let's figure out what we ended up getting. So on my calculator, I'm typing in some numbers. 1.52 times 39 times 2, that's a 1, 278, enter. And then I'm going to divide by 1.3, and I'm going to divide by 46. And I get a number 276. Let's just call that 276. And once again, how do we know the unit? Well, let's see. Atmospheres cancels. Milliliters cancels. Kelvin is not canceled. And so that's how I know the unit's going to be Kelvin. All right, next question that we got a request for. I'm going to flip over to the honors section really quick. I'm going to look at the honors page, and I'm doing number 3 in part 1 right here. Right here. Right. Please stop being stupid. Nope, that's not what I wanted. All right. Right here. Phew. I'm going to flip over on here as well. All right. A gas at 89 degrees Celsius. That's useless. We don't want 89 degrees Celsius. I'm going to go ahead and do it. I'm going to add 273. That's going to be 362 now. So this is now 362 Kelvin. Occupies a volume of 0.67 liters. Assuming pressure does not change. So what does that tell us? Okay, no pressure in equation. Okay, there's going to be no pressure. Oh, look, one of my friends is playing Fallout 4. Wish I was. So no pressures in the equation. At what temperature? So hey, that's our target. Temperature is what we're looking for. In Celsius, that's kind of annoying. We'll have to do a conversion at the end. Will the volume increase to 1.12 liters? All right, let's write all this junk out. So step number 1, let's see what they gave us. Well, we know T1 is going to be 362 Kelvin. I know that the volume 1, which remember guys, 1 and 2, if you want to write it as 1 and 2, that is fine because that's how they do it on the equation sheet. The way I always think about it is I for initial or starting, same thing. Okay. And then 2, I think of it as F as the final or the ending like value. So you think about it however you want. That's how I'm going to think of it. So V1, they gave us 0.67 liters is what we started with. New volume, V2 is going to be 1.12 liters. And step number 2, what the heck am I looking for? Well, I know I'm looking for T2, and I really want to have it in degrees Celsius. Okay, so now that I've done all that junk, it's getting really dark outside. Can you check the radar and see if it's going to rain? Sorry, I'm really concerned about rain because there's a bulldozer right now working at my house, and I'm stressed about it, just a little bit. All right, so what I told you guys to do is, in my opinion, it is always useful to just write out this whole thing whenever you're doing one of these gas law type problems, not ideal gas law. This is not going to help you with ideal gas law. But see, when you do this, you don't have to memorize everywhere.
It's pretty big.
Pause.
Pretty big.
Storm.
Storm.
When.
Right.
Great. Well, that's annoying. Anyway, guys, sorry about that. So, here's the thing. Always start with combined gas law. You don't have to memorize it because they give it to you in the reference tables. And then, based on what they've given you, okay, based on what they've given you, you actually look and see, you know, okay, what stays constant? Pressure. I just said there's no pressure in the equation. So I'm just going to eliminate pressure. Pressure. And then you've got the equation you want. Okay. Yep. See, Emily. So, and if you need more, just let me know. All right. So now that we've got this, let's plug in some numbers. Step number 4, V1. Oh, sorry, we didn't isolate what we were looking for. We're looking for T2. So I don't know. We can just do this. Once again, I don't like T2 to be in the denominator. So when I do it this way, it works a little bit better, in my opinion, for students. Because then you can say, oh, well, now I've got to get that stuff on the other side. So how about this? Long story short, we're going to end up having this as our equation. There we go. That's the final. That's our answer. I don't like how I wrote it, but that's the answer. Okay, so let's just skip that part for right now. If you really need help with algebra, I can help you with it later. But for now, let's just keep things moving. So there we go. This isn't an algebra class after all. All right, step number 4, plugging everything in. T2 is what we're looking for. V2 is going to be 1.12 liters. Okay, T1 is going to be 362 Kelvin. And this is all going to be over V1, which is 0.67 liters. Okay, so everything's where it needs to be in the equation. So now you plug everything in your calculator, and you're going to get some type of answer. So 1.12 times 362 divided by 0.67, and I get 605. but that's 605 Kelvin. How do I know it's Kelvin? Look at the units. We had liters, we had liters. Kelvin is what we were left with. Okay, so it'd be Kelvin. It wants it in Celsius, so all we're going to do is subtract 273 from that. And so now we get T2 is equal to 332 degrees Celsius. There you go. All right, not too bad. All right, so next, looks like we're looking at part 2, number 3. If you guys do have questions, just be typing them. I'll get to them as soon as I can. So I'm going to look at part 2, number 3. Let's see. Here we go. Determine the temperature in Celsius. Ugh, got this crap again. Temperature in Celsius of 2.49 moles of gas contained in a 1 liter vessel at a pressure of 143 kilopascals. Whenever you guys see moles, that's a big flashing light saying you need to use ideal gas law. You need to use ideal gas law. And so the same is true here. We're going to use ideal gas law. So with that in mind, I know the sorts of things that I'm going to be looking for. So P, did they give it to us? Yes, they did. 143 kilopascals. V, did they give it to us? Yes, 1.00 liters. N, 2.49 moles. Okay, and so I know what you're thinking. Well, Mr. Aaron, is that everything? Because that's all the numbers. Guys, remember, you always have the gas constant. You just need to figure out which one to use. And the thing that's going to determine that is right here, kPAs. So I'm going to look at my gas constants, my R's, and I'm going to see, oh, does one of them have kPAs in it? Yes, it does. So this one, for this problem, I'm going to use an R value of 8.314, and it's going to be liters times kPa over moles times Kelvin. So that's the one I want to use because it has kPa, it has kPa. All the units are going to work out. And you'll know if you didn't use the right R value because when you get to step number 5 and you're trying to figure out what units don't cancel, it'll be pretty obvious that something's gone kind of wrong. What are we looking for? We're looking for temperature. And again, we're going to need it in Celsius, but we'll do a conversion later because you're going to get Kelvin after you do the math. Step number 3, let's write this out. PV equals nRT. I know I'm looking for T. So if I divide by nR, that cancels them. I'm going to divide this side by nR as well. And so I end up getting T equals PV over N times R. There you go. Step number 4, plug all this junk in. T is what I'm looking for, so I'm just going to rewrite it. Pressure is 143 kilopascals. Volume is 1.00 liter. And I'm going to divide by number of moles, which is 2.49 moles, times R, which is 8.314. All this junk, liters times kPa divided by moles times Kelvin. Okay. And then step number 4. Step number 4. Here we, or sorry, 5. We got to do all the math. So I'll do 143 times 1. I'm not going to do that. Divided by 2.49 divided by 8.314, and I get 6.9. Now, units, once again, guys, take a look. Take a look. Don't just guess. We had kilopascals. Kilopascals canceled on the bottom. Liters, that canceled on the bottom. Moles, that canceled. So what we're left with was Kelvin. Now, Kelvin is not what we want. We want degrees Celsius. So I'm going to subtract 273, and that's going to give me a new answer. So temperature is actually equal to negative 266 degrees Celsius. That is really cold. All right, there's that one. Test says let's also do number 5 in part 2 as well. That's this one right here, I reckon. Let's take a look. I hope this is helping you guys. If it is, I don't know, give me a thumbs up or something. If you do have questions and you want to look at something else, just let me know. Add it to the list. Let's take a look at number 5. What is the Kelvin temperature? Oh, isn't that nice? Required for this many moles of gas to fill a balloon to that volume under that pressure. So this one should be okay. Shouldn't be that bad. So let's see what we got. I just use green, so I'm going to use bright blue. Let's see what they gave us. Number of moles, 0.0470 mole. Volume is going to be 1.20 liters. Pressure is going to be 0.988 atmospheres. Okay, and my R value that I'm going to use needs to have atmospheres in it because that's my unit for pressure. So I'll say, all right, well, I'm going to use this one then. 0.0821. Okay, and that's going to be liters times atmospheres over moles times Kelvin. So there we go. Step number 2, what are we looking for? Well, it tells us what is the temperature going to be equal to, and they do want it in Kelvin, and that's something we can easily handle. So step number 3, let's see here. PV equals nRT. I know I'm looking for T, so I'm just going to say, all right, well, this is divided by N times R. I'm going to divide this side by N times R. That'll cancel what I don't want. And so I end up getting T equals PV over NR. Again, just algebra. It's the same two things that I've been saying since the beginning. Whenever you're doing algebra in this class, if you want to get rid of something, do the opposite. So if you're adding, subtract it. If you're multiplying, divide it. That cancels it. And this is step number 2. Whatever you do to one side, you do the other side. And you keep doing that until you get what you want by itself. Okay? And that's what we've done. So step number 4, I'm going to plug all these numbers in. T is going to be equal to my pressure, 0.988 atm, times my volume, 1.20 liters. And this is all going to be divided by 0.0470 moles times R, which is 0.0821 liters, atmospheres over moles times Kelvin. So now, sorry, it got clipped a little bit, didn't it? Let me scooch over just a hair. There we go. So now step number 5. Let's see what we ended up getting. So in my calculator, I'm doing 0.988 times 1.2. I'm going to divide by 0.047. And I'm going to divide by 0.0821. And I end up getting an answer of T equals 307. And let's check what the units are going to be. Okay. Atmospheres, it cancels. It's on the top and on the bottom. Liters, it cancels. It's on the top and the bottom. Moles, it cancels. And what am I left with? But Kelvin. So, hey, that was the answer. That's what we wanted. We wanted temperature in Kelvin. And everybody should be happy with that. That is a really bad number 5. Let's try this again. There we go. That looks slightly better. Next one, number 8 in part 1. Let's go take a look. Oh, yes. Did we do that one? Except it was on the other worksheet. Did we do this one? Yep, we did that one earlier. This is actually the same as number 5 on the other worksheet we were going over. So honestly, I can go over it again if you didn't see it, and type me if you want me to do that. But honestly, you can just rewatch it and go back. This is the same as number 5 on the standard worksheet. So I've already done that in the stream today. So I've done that one. Are there any other questions that you guys have? I am here to serve, even if it's just 3 of you. I'm hoping that more people watch this later. But are there any other ones? Just look through your work and say, oh, can you go over blah, blah, blah. If you have a question about anything, now is the time to ask while you have a teacher here. I'm going to take a look at the radar real quick. But guys, type at me. If you don't have anything that you want us to go over, I'm going to move on to something else, which is leaving. Yeah. It's really raining heavy in eastern Tennessee. Okay, we're back to 4 people. So if you just joined the stream, welcome. Tell us something that you want us to go over. Anything. I'll go over it. Okay, good, Egypt. And again, if you want to rewatch it, you can. Anybody else? Any questions? Anybody? I'll give you 30 more seconds, and if nobody says anything, I'm going to go ahead and end the stream. Okay. 20 more seconds. Giving you guys another chance. All right, guys. Thanks. Ooh, glad that bottle was closed. Thanks for joining. If you do have questions, email me, remind me. Thanks for liking, commenting, and subscribing. And I will see you when I see you.